I'll write down an example on a double integral. So if you have double integral f of x, y, dA, and we have some region D here. And if we want to switch to the integral in terms of u and v, then the price to pay is going to be Jacobian, which is kind of your similar to what we have in calculus 1, but it's determinant, absolute value of it. Now we have f of, and make sure you can switch here to u and v. So we have x on u and v and y on u and v. So switch to do u substitution. So express x in terms of u and v, express y in terms of u and v. Okay, and that's new region. That's an image of your original image. So where Jacobian, that is Jacobian from x to y, is we're going to treat x as a function of u and v, so derivative of x, partial derivative with respect to u, partial derivative of x with respect to v, partial derivative of y with respect to u, partial derivative of y with respect to v. All right, so let me try to do a couple examples related to this. Say we want to calculate integral of x times y, double integral, x times y dA, over region D, where D is bounded by straight lines y equals x, y equals 3x, and two hyperbolas, x times y equals to 3, and x times y equals to 1. Okay. So let's have a look on what is going on here. Just looking at what you have, and if you want to do substitution, then you almost immediately see that 1 over substitution, which you kind of want to make as u equals to x times y, because that is going to force u equals to 3 and u equals to y 1, which are going to be extremely nice bounds. Okay. Now, if I want to find what I want to do for these two guys, and then this I can rewrite as y over x equals to 1 and y over x equals to 3. So that is kind of telling me that I probably want to do substitution v equals to y over x, because then I will have two nice equations, v equals to 1 and v equals to 3. Okay, so that's what I will do if I will do substitutions. But before I do that, let's firstly, I guess, look at our regions before we do anything. So we have straight line x equals to 1, y equals to x. We have straight line y equals to 3x. Then we have parabola xy equals to 1. Xy equals to 1. And we have hyperbola xy equals to 3. Okay. So if I try to set the limits for this region in terms of x and y, it will be extremely difficult. It's possible, but it will take some efforts. So I'll have to break that region maybe in 2, 3, maybe 4 pieces, and each piece will be type 1 or type 2 regions and do what I have to do. But again, as we mentioned, in terms of U and V, it's going to be so much easier. So now if I switch to U and V, the ones which we've suggested, then our equation in terms region in terms of U and V is going to be so much easier, so much better. Because xy equals to 1 and xy equals to 3, we transform that into u equals to 1 and u equals to 3. So xy equals to 1 becomes that u equals to 1. Xy equals to 3 becomes u equals to 3. Because that's what xy is. Xy is u. Y equals to 3x and y equals to x. We change them into y over x equals to 3 and y over x equals to 1. So in terms of u and v, that is v equals to 3. So v equals to 3. And v equals to 1. And now we have a nice region to work over, okay? So as we mentioned, that u is going to be between 3 and 1, v is going to be between 3 and 1. So instead of having complicated region, we moved that region, which was given to us by two complicated curves, straight lines, and hyperbolas, into simple one, which is now a rectangle. Okay, now let's calculate the Jacobian of it. So let's calculate the Jacobian. I'm not going to be calculating Jacobian itself. I'm going to be calculating a Jacobian in terms of u going to v. So what I will do is I will calculate uv to xy. I recall that u equals x times y, and v equals to y over x. Derivative of x with respect to y is going to be with respect to x is y, derivative of u with respect to y is x, derivative of v with respect to x is -1 over -y over x squared times 1 over x. And we calculate in determinant of that expression. So we're going to get y over x plus, I reduce that, plus y over x. So we're going to get 2y over x. So that. So what we concluded is the following. Now with Jacobian, which is, if you want to go from x to u, if we calculated Jacobian from u to x, and if we want to calculate Jacobian from x to u, xy to uv, then we have to take a reciprocal of what we just got. So we're going to get x over 2y. And for purposes of our substitution, we want to write that in terms of u and v, because we want to have our new integrals in terms of u and v. So what we're going to get is 1/2. You can see here we have x over y. If possible, often we'll do solve x in terms of, and find x expression for x in terms of u and v, expression of y in terms of u and v. For this Jacobian, we don't have to, because you recall that y over x is v, so x over y is 1 over v. So we're going to get 1 over 2v. And that is our price, which is Jacobian. Now we are ready to set up for integral. Because you remember, we're going to get easy region, 1 to 3, 1 to 3, or for u and v. Then we have our price. And then our integral is x times y. And x times y was our u. And now we have extremely easy integral to find. Extremely easy, basically for these classes, it's easy as it gets. So you split it, it's a rectangular region. So 1, 2, 3 u du, 1, 2, 3, 1/2, 1 over v dv. So we're going to get 1, 2, 3 u squared over 2 from 1 to 3, 1/2 natural log of v from 1 to 3. So we're going to get 9/2 minus 1/2 is 8/2, which is 4 times 1/2. ln of 3 minus ln of 1, ln of 1 is 0, so ln of 3. So 2 ln of 3. So that's what we got for this integral. Find the area of region inside of ellipse x squared over a squared plus y squared over b squared equals to 1. So we have our ellipse. Okay. So area equals to double integral 1 dA and over region D. Okay. The substitution which I want to do here is, instead of having x squared over a squared plus y squared over b squared equals to 1, I wished where x squared plus y squared equals to 1. So I want to get from this one, I wish to get u squared plus v squared equals to 1. So that will kind of tell me the substitution which I want to make is u squared equals to x squared over a, so u equals x over a, and v equals y over b. So we're going to do substitution. X equals a times u, and y equals b times b. So we can easily calculate Jacobian here. Partial derivative of x with respect to u, partial derivative of y with respect to u, and partial derivative of y with respect to b. A 0, 0 b, so a times b. So in terms of uv, our region again becomes u squared plus v squared equals to 1. That's new region, let's call it E. So what we're going to get is, I'll move on to the next page, double integral of that new region E. We have our original function 1, price to pay a times b, du dv. And this one is supposed to be easy to finish if you like. Double integral, take ab out, 1 du dv e, and you realize that if you have the area of unit circle, u squared plus v squared equals to 1. So we're going to get an area of unit circle is 5. So 5 times a times b. So that's what we're going to get in this case. Or if you like, you can feel free to switch, I don't know, to polar coordinates or anything like that to finish it up.